Hello everyone, this is lecture 6. We continue with where we left last time. So we were doing probability basic stuff, introduction. Let us see. And we stopped with the quiz, and there were 2 questions. So let us continue with the examples. So the first example is throw 2 dice, and this was part of the quiz last time. So I will continue with the solution here. Throw 2 dice, and the event is bigger number on the red than the blue. So there are 2 dice. One is red and another is blue. And what we are defining as a favorable outcome is that a number that appears on the red is bigger than the number that appears on the blue dice. Okay. So the question is, what is the probability of this event? So we can write the sample space. So this is the sample space. Okay, which is the set of all possible outcomes. So this is the set of all possible outcomes we can expect when we throw 2 dice. So this is the sample space. And event is something we have defined. So this is something we are recalling. Probability space is set of all outcomes and event is some favorable outcome. So for this example, the favorable outcome is to expect bigger number on the red than on the blue. So if we list out the favorable outcomes out of these all set of all possible outcomes, then we can put them in a box to identify which of these are favorable outcomes. So these are the favorable outcomes where the number on the red is bigger than the number on the blue dice. Okay. So for example, these all are these cases, the rectangle. And we have to count them because probability will be number of favorable outcomes divided by the total number of outcomes. Total number of outcomes is 6 times 6, which is 36. And then we have to count these cases where the number on the red die is bigger than the number on the blue die. And this comes out to be, I believe, 15. So hence the probability will be 15 over 36. Okay, of this event. Another question that I asked in the quiz is toss a coin n times. Okay, so toss a coin n times. And when we toss a coin n times, we expect the outcome to be sequence of n bits. So first time I tossed a coin, second time I tossed a coin, third time, and so on. And then I'm doing it at the nth time. So this is like n times I have tossed a coin. So I get a sequence of n bits. So this is a sequence of n bits, right? So the total number of outcomes, what do we get in this case? The total number of outcomes, it's either head or tail. To another next step, if I toss the coin, it's again head or tail. So again, the possibility is 2, 2, 2, and then so on. It's 2. So it's 2 to the n. Okay. So in this case, the cardinality of the sample space is 2 to the n, or in other words, the total number of outcomes is 2 to the n. Assumption here is indeed the fact that each of these are like the outcomes are like equiprobable. Okay, so they happen with equal probability. There is no bias. So in this case, the probability of all heads, if we count probability of getting all heads, so all head will happen when we have head n times. So this is n times. We have got head, and this is the only case where we get all heads, right? That's the only possibility. So the probability of getting all head, if we define the event as probability of all heads. Okay, so probability of sorry, the set of all heads, right? So you remove this, so set of all heads, and the probability of this event where you get exactly all heads. So there is only one in this case because this is the only case we have all heads, and then the total number of outcomes we had was 2 to the n. So this is why I have 1 divided by 2 to the n. Now we define some other event, let us say, so this is just an example. Consider an event where the first bit is equal to the last bit. First bit is equal to last bit. So naturally we will ask, what is the probability of this event when the first bit will be equal to the last bit? Okay, so you are tossing a coin n times, so you can start with either head or tail. Let us say tail, tail, head, tail, head, 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 tail, so on, and then you may end up with, let us say, head in the nth toss. This is your n bit in the sequence. And another case could be like head, 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 tail, tail, head, tail, so on, and you end up with, let us say, tail. Okay, another possibility would be tail, head, and so on, and let us say you end up with the tail, and another possibility could be head, head, tail, tail, and then let us say you end up with head, and so on. So there will be so many ways you can do. In fact, there are like 2 to the n outcomes. So out of these 2 to the n outcomes that you are you may get, what is the probability that the first bit, so we define this as a bit, right? A bit of answers, a bit. So the first bit in this case is let us say head. Okay, so what is the probability that the first bit or the head is the same as the last bit that you got, or in this case it could be also the tail, and then you got the tail again. So this is again a counting problem, and most of you might have given correct answer already. So here we have to find how many possibilities could be there in this event where the first bit will be equal to the last bit. So this now it's intuitive in our head what could be the case. Let us see the answer. So number of possible cases, as I said, in this case, so what we can use is use some star in this case to denote that it could be any possibility for the star. Okay, so we use a generic star here to mean any of the head or tail. So if we count those cases, so a sequence may have either this form, a sequence may be coming up with either this form, or either this form. And anything is possible when we have these star. Okay, so these are the possible outcomes we expect. And what we observe is that in half of the cases, okay, so in half of the cases, the first bit is equal to the last bit. Okay, that's what we observe here. In all these possible cases, what we observe is like there are half of the cases like this, and this cases is where first bit is equal to last bit. So, and then these are those cases where first bit is not equal to last bit, and we know that these are like equal number of cases, right? So these are all equal number of cases, and out of these 2 cases have the first bit is equal to the last bit. So from here we can say that that in the probability of the event will be half. Okay, because out of all the 2 to the n, okay, out of all the 2 to the n outcomes that you have listed here, out of these, in half of the cases, okay, so in half of the cases which are these and these cases, you are having first bit is equal to last bit. So if we divide by, if we go by the counting, then 2 and 2 to the n, 2 to the n gets cancelled, and then we get half. Okay, so the answer should be half. Okay, so I would like to remark on counting. So the question is, does probability always boils down to counting? Okay, is it true that in many cases probability boils down to counting? Okay, so that's a fact. However, there could be like non-uniform distributions also. For example, a number of heads may be more likely than the tail. Okay, so this like it's not really equilikely. We will also study continuous distributions where counting doesn't work. Okay, so counting doesn't make sense in the case of continuous distributions. So we have to do something different. Okay, so in the case of continuous distributions, so in the continuous case, just to give you an idea of what could happen. So this is the continuous case where this is an closed interval. If you remember in the first class, this is a closed interval that takes all the real numbers from 1 to 2. And we are asking what is the probability that the number 1.5 is picked in this closed interval 1 to 2. So if we go by the counting argument, then the event that you define is to pick the number 1.5, and the sample space, if you consider all possible points in the interval 1 2, then it's infinity. In fact it's bigger and bigger infinity actually. So from the countability things that we have studied, the set of real numbers between any closed interval is a bigger infinity. Okay, so we have seen like a set of integers have this, and then we have alpha, which is the higher level of infinity, and so on. So this denotes the infinity for the natural numbers set, and this is for the real number set. But any real number set is, in some sense, you can like identify them with the real line. Okay, because there are like, you can identify some map, okay, bijection and so on, so that but you cannot identify bijection from 1 to natural number. Okay, so it is a bigger infinity. And so, but even if you consider this as this infinity, it doesn't make sense. That's what I'm trying to say. So probability of the event is what? 1 divided by infinity. So this is like 0. Okay, exactly 0. Okay, so if you go by the counting argument and take the number of favorable cases divided by the total number of cases, then the counting argument, I mean, it will always be like 0. Okay, so so these things won't make much sense. Okay, so we will see. We will get into the continuous case, obviously. So now let us look into some application with where probability is involved. So let us see this this video. Okay. So this is the slow motion of the particles are falling, okay, from the top, and there are some beams in at the bottom, and then there are some dividers there, and the particles fall, and then they hit these dividers, and then they fall, and after the fall, this is what you see. Okay, So this is what you see in the after the fall. Okay, so the question is, what is happening here? Okay, and does probability has any role in this? Okay, and why the distribution of the why the distribution of these balls, these small marbles, is like this? So why it is centered more towards the towards the center of these towards the center of a central beam? Okay, and then it decreases as you go away from the center. Okay, so this is called Galton's board, and we want to study this. Okay, and it probability has a role to play in this. Okay, so let us see this schematic illustration of the Galton board. Okay, so this is the Galton board, and these were the marbles that fall from the top, and it goes via these small dividers, and then they fall into one of the bins. Okay. So this is Galton board after Sir Francis Galton, and the set of red marbles are allowed to fall. We observe the distribution of the marbles after the fall. The question is, why do we have more marbles in the middle? Okay. Does probability have any role in this distribution? Can we prove that the distribution will look like this mathematically? So can you prove that it has to be like this? Does Pascal triangle has anything to do with this? Let us analyze this in detail. Okay, so we can remove the background thing and we can represent this graphically. So we assume that at each level the beams are split evenly. The probability that the ball hits the current beam, which is the sum of the probability of this ball hitting the left and the right beam above. Okay, so we are expecting that these guys are like evenly distributed, are at equal distance from the center, and then these guys are splitted at equal distance. Okay, equal distance. Okay, that will create the case of equiprobable. Okay, so these are equal distance and so on. Okay, and the ball falls from here, so we can fix for a moment that one ball falls from here. Okay, and it falls, and the probability that the ball will hit the first one is 1, because that's the only way, that's the only gap that you have, and then you have a container for the balls here. Okay, so the first all the balls will definitely hit this this first divider. Okay, and that the hitting probability of hitting that is like 1. Okay, so let us start from here actually. So ball entered here, but this is the first bin it divider it hits, and then what is the probability that it will go in left or the right direction? So from here onwards we can say the probability of going to the left and probability of going to the right is half. Okay, so this half is here and this half corresponds to this, and then it will go down, and it will go down. Now it has to split further into 2 halves. So the probability of getting into this and the probability of getting into the right one and then the left one is again half of that, right? So it's like half of the half, and then if you are coming here, then this is again half of the half. But then this guy also has some probability of coming from the other way. So here you had half. Okay, and then from this half gets split into half times half, and this half again splits into another half times half. Okay, so you have another half times half here. Okay, so half times half. So you see this half times half is also contributing to this half times half. Okay, so for this guy, what we have is 1/4 that is coming from the left contribution and 1/4 that's happening from the right contribution. So this is like 2/4. Okay, this is 2/4. So this way you can fill up this. Okay, from here onwards, let us say here you had 1/4. Now this 1/4 has to split in half this way, half this way. This is like half of 1/4, and this guy also is half of 1/4 plus whatever is coming from this way. Okay, so there is also contribution coming from the right. So you have to add those probabilities. Okay, so this is what it looks like, and it can remind you of the Pascal triangle and the reason why we were studying the Pascal triangle. So we start with probability half, and then as I said, explained, it will be half, and then this is half of the half. So this is 1/4. This is half of this half, so 1/4, and then another half of the half, 1/4. So this is like 2/4, and this way you can fill. But the question is not to manually do this, but to understand the pattern. So if we look into the pattern, this is looking similar to the Pascal triangle, except that you have the denominator here. So if you forget the denominator, then it is like a Pascal triangle. Okay, so you have 1, 1, 1, and then like 1, 2, 1. Okay, so you have like 1, 2, 1, and then you have like 1, 3, 3, 1. Okay, so this is a Pascal's triangle. So and what we note about the denominator is like the denominators are nothing but the sum of the rows of the Pascal's triangle, right? So sum of the rows of the Pascal triangle was 2 to the 0, okay, and sum of the row again is 2 to the 1 and 2 to the 2 and so on. Okay, 2 to the 3 and so on, and these guys, some are going in the denominator of these when we are computing the probability. So these denominators are nothing but the 2 to the power level that you have, right? So this 2 to the 0 level, and then if you go to the second row, the first row, let us say 0th row, you start with 2 to the 1, and then you divide by 2 to the 2 and so on. So, and another thing we recall is in Pascal's triangle, these things were identified as n choose k, if you remember. Okay, so that's the way we have n choose k, or this is same as n choose n minus k. So there was a symmetry in the Pascal's triangle. So these guys will actually be fine. Okay, same. So the probability of a ball falling from the top and hitting some beam now can be calculated as n choose k and then 2 to the k. Okay, so this is what we have here, or 2 to the n. I made a mistake there. The denominator is like, so this is what we have for any place that you look at. This is how you will identify the probability. Okay, so that was about choice tree and how probability gets distributed over time in those scenario where you have like tree like decision tree, and there are cases, as I said before, where you could have non-equiprobable outcomes. For instance, let us say the dice is skewed. Okay, so this is a skewed dice. Okay, so here the probability of some number may not be the same as the other. So maybe the 4 is more likely here than 1 or so on. Okay, because maybe number with 1 may have very
Sir,
small
can you go back to the previous slide? I
small
wanted to know
area,
something.
so it may be unstable. So when you throw, there may be more chance that it will fall on the broader side when it falls at the bottom is broader, and so then the probability of getting these will depend on the how fair the dice is, right? So on the left we have a skewed dice. Will our previous definition of calculating probability work? Unfortunately, not, because we have to deal with the skewed cases. But even in the skewed cases, The only thing is, as I said, the frequency of the outcomes can be different. So for example, the frequency out of 10 throws that you do, the frequency with which you might get one will be very less, let us say only 2 times. Frequency with which you get two may be a little bit higher, and so on. So if you run this trial uh, many times, then you will see that they will settle down to some frequency, okay, eventually. So asymptotically, they will settle down to some probability, okay. It is just that they may not be the same, okay. So probability of 1 over time may be very less than probability of 4 or so on. So let Pi denote the probability of the ith number. If we throw the dice long enough, the frequencies will stabilize. That's what we are expecting. So for example, probability of getting an even number will still be like P2 plus P4 plus P6. But the only thing is like P2 may be much greater than P4, and P6 maybe less than much less than P4. But overall probability of an even number is indeed like the sum of the probabilities of P2, P4, P6. Also, we know that the sum of all the probabilities should sum to 1 because there is nothing else that we are expecting. Even though the dice is skewed, if we sum up all the probabilities of all the outcomes, it is going to be 1. Okay, so because nothing else, there is a possibility of nothing else. It's not going to fall on the edge. That is what not we are expecting. Okay, so the sum will still hold to 1. Okay, now let us understand few things with Venn diagram and so on. My point is to go into a mutually exclusive and so on, and then do some examples and so on. And what happens if your event have some intersections and so on. So this is my plan now. So let us see through a fair die 1, and the sample space is 1, 2, 3, 4, 5, 6. And let us consider some event like it is shown in the Venn diagram. In the Venn diagram, you can see that I have defined an event A, which is 1, 2, 3, and this event A is also shown in the Venn diagram. And we have also defined an event B, and which is the number 5 and 6 on the die. Since the die is fair, we have P1 plus P2 plus ... P6 is 1. So that's something we know because there is nothing else that is expected to happen. So all this must sum to 1. Let us define the probability of the event A. Well, not defined, but this is what it is. Probability of event A will be the sum of the probabilities of P1, P2, P3. And probability of B will be P5 plus P6. Now consider the event of probability that A happens or B happens. Okay, so either happens. So which is nothing but when someone asks you like this, probability of event A or B, then it's like as a set you have to take the union. So if you take the union, then this is what you get: 1, 2, 3, 5, 6. Okay, 4 is left out. The 4 is left out here. So that's the probability of event of either A or B happening. And in this case, when we have to calculate probability like this, probability of A or B, and then we write like this: probability of A plus probability of B. Now there is already a question here, like why did we add the probabilities of A and probabilities of B when we had to calculate probability of A or B? Okay, and individually this is what we have. This is probability of A, this is probability of B, and that's what we have added. So a natural question here is, when are the cases we can add probabilities of two events? Okay, so that's the question I'm asking here. Why probability of A or B happen to be probability of A union B? If you look into the set theory, from set theory, if you look into the cardinality of A union B, then it is clear that the cardinality A union B is cardinality of A plus cardinality of B for this example. And this happened because A intersection B was empty. Okay, that's why you could add. Okay, and actually same thing is happening here. Okay, so we can translate this into into probability language that we can do this if the events A and B are disjoint. Okay, if the events A and B are disjoint, then we can do this. So this is just an illustration from the Venn diagram, and we have seen a little bit of this in the beginning also. Okay. So when are we allowed to add probabilities? Well, as I said, we are allowed to add probabilities when we have like this disjoint disjoint events. Okay, so we have seen this before. I'm just so I will so two events A are said to be mutually exclusive if they have disjoint set of outcomes. And if A and B are two mutually exclusive events, then probability of A union B is probability of A plus probability of B. Okay, we have seen this, and then this also we have seen, and the probability of the complement is 1 minus probability of A. And same thing now can be extended to n number of events. So probability of A1 to AN are called mutually disjoint events if we can sum up all this. Okay, we have seen this. And it also holds for control B infinite. Now, let us try to answer this question now. So up to now, we understand what are disjoint events and so on. And implicitly, we now also understand what could be a non-disjoint event. A non-disjoint event will be where A intersection B is not empty, right? So A intersection B is not empty, they intersect. Those events will be non-disjoint or not mutually exclusive. So let us try to build on this. In a cricket tournament with 4 teams denoted by A, B, C, D, Team A has 20% chance of winning, while Team B has 40% chance of winning. Okay, so what is the probability that A or B will win the tournament? Okay, so the probability of the event A, so A is winning, right? A wins, okay, and B is the event that B wins. Okay, so these are the events, and what you are given is probability of A is 20%, so 20 by 100, so 1 over 5, and probability of B is given to you, and which is 40%. Okay, so this is 2 over 5. Okay, now the question that is being asked here is probability of A or B. So when you say or, then it's union. Okay, is what? Okay, so what do you do in problems like this? Right, so problems like this, one of the things we have to see is like whether these events are mutually exclusive, because so far what I know is that if A and B are mutually exclusive, then this is nothing but probability of A plus probability of B. So if A and B are mutually exclusive, in other words, A and B don't intersect. So does A and B intersect? Okay, so does A and B intersect? So that's the question we are asking. Well, can it happen that so intersect here means like this, right? So can it happen that both A and B are true? Well, it's a tournament, and assuming that we must have a winner. Okay, so this will never settle in a draw. Okay, so in a tournament we always have some kind of winner. Okay, well, it did not happen all the time like this. In cricket tournaments, sometimes people had a draw, especially if it is a like, well, even in like one day or test matches, sometimes it happens that, but it may happen that they will share or something, a trophy or something like that. But assuming that the tournament must have a winner and there will be a way to break the tie, like it happened in the last World Cup, where things went up to the super over, and then it happened once again. So it was really, yeah, but they had to really break the tie. Eventually, England won, right? So yeah, it won in a really strange way. But anyway, so so assuming that there will be a winner, okay, we will not settle for a draw. So it is not a mix. It is a mutually exclusive event. A and B cannot happen together simultaneously. So in this case, we have to identify in problems like this You have to identify, and of course the question has to also make it specific that there can be a draw. So then in those cases you can add. Okay, you can add, and there is nothing for us there is nothing to do with what happens with C or D. Okay, because we are directly given the probability of A, so we do not have to compute the probabilities of A and B, because then probability of A and B does depend on the probability of C and D. But in this case, the probability of A and B is already handed over to us. We simply had to establish whether these events are mutually exclusive or not, and it turns out it is exclusive because only one can be a winner. So in this case, A and B are disjoint, so I can add the probability. So probability of A union B is probability of A plus probability of B. So in this case, it will be 1/5 plus 2/5. So this is 3/5. Okay. Okay, so let us look into another example. So suppose we know the following, that there is a 50% chance that it will be hot today. Okay. So, and there will be 30% chance that it will be hot tomorrow. So let us say the event A. So when you see problems like this, you start writing the events. Okay. So let us say the event is that it will be hot today. And let us say define the event B to be hot tomorrow. Okay, so event A is hot today, event B is hot tomorrow. Now the other thing is given to you is, so probabilities are given to you. So probability of A is 50%, so this is like 1/2, and probability of B is 30%. So this is like 3/10, and there is a 10% chance that it won't be hot today or tomorrow. Okay, it won't be hot today or tomorrow. So these cases can be obtained from this. So this case is like hot today or tomorrow. So this is like probability of A union B. Okay, so that is, oh, okay, so this is negative of that. So let me define that we write this in negative way, right? So negative in the probability case is what? So this is probability of A union B complement. Okay, so this is, it won't be, it's saying, right? So A union B was, it's hot today or tomorrow, and won't means like complement. And this is given to us to be 10%. This is 1/10. Okay, now we have to answer the following, and this is like probability that it will be hot today or tomorrow. So the question was probability that it will be hot today or tomorrow. So probability that it will be hot today or tomorrow is A union B. And we know that this is 1 minus probability of A union B complement. Okay, for any event A, probability of that event is 1 minus probability of that event complement. So that can be computed. So this is 1 minus 1/10. So this is 9/10. Okay. And then the second question is probability that it will be hot today and tomorrow. Okay, so this is like A intersection B, right? So probability that it will be hot today and tomorrow. So when someone asks you today and tomorrow, then you take intersection of the events. Okay, so this is what? So far, what we know is probability of the identities that we are familiar with is probability of A union B is probability of A plus probability of B if A intersection B is empty. So this is what we know, right? So this is what we know. But here what is being asked is it will be hot today and tomorrow. So it's like intersection. Okay. So what will be this? Okay, so we are leading to this. I have not told you what would be this, but we want to tackle problems like this. Okay. So from set theory, you can guess what was the usual case, right? So A union B was probability was cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay, so this is what we know from set theory, and actually in probability you can you have the same thing. You just add P here. Okay, so you just add P here, and so on. So from there you can compute the probability of A intersection B. Okay, because probability of A is given to you, probability of B is given to you, probability of A union B you already found out. So from here you can get probability of A intersection B. Okay. So and then so this can be found out, and again this can be found out. Okay. So some negations, complement, and so on you have to do, and this is easy. So so what we are leading into, as I said, is the cases where we have non-mutually exclusive events. So does this relation hold? So what should hold here if A and B are not really mutually exclusive? So let us consider the two examples where A and B are not mutually exclusive. In other words, A and B do intersect. So for the events A and B, which relation one holds? Okay. So this continued with this example. So let us say in this example we have probability of A, which is P1, P2, P3. Probability of B individually is P3, P4. Now if we want to calculate the probability of A union B, then probability of A union B, if I do union, then there is a duplicate 3 here. So 3 shows up once, right? So that duplicate is removed, and then I have 1, 2, 3 is sum of these probabilities of P1, P2, P3, P4. So if we have to guess a formula here, then it was indeed probability of A plus probability of B, but then there was something in the intersection that we were supposed to remove, because it was counted here also and it was counted here also. So we could have removed probability of 3, one of that. Okay, so that is this was nothing but probability of A intersection B. So one of that we have to remove, so that we don't get the duplicate here. Okay, so that's what we did. So using this, we have that probability of A union B will be probability of A plus probability of B minus the probability of A intersection B. And this is coming, so this proof, I mean, it's similar to the inclusion exclusion principle one could do. So we can write down this inclusion exclusion principle in a general form. Let us say if you have 2 events, then this is what inclusion exclusion principle says, but you may have also 3 events. Okay, so in that case, this is the inclusion exclusion principle. It's just that now we have probability instead of the cardinality. In general, for n events, we have these results. Now, let us now see what is the meaning of discrete probability. Sample space can be of 2 types. It could be either discrete or continuous. In discrete probability models, we compute the probability of events by adding all the probabilities, right, in the corresponding outcomes. If they overlap, then we remove and so on. Okay. In continuous probability models, we will need to use integration instead of summation. Okay. So what is the probability that if I draw a coin, what is the probability that if I draw a coin randomly from this rectangle, then it happens to come from the circle? So in this case, the favorable in this case, the probability of an event happening of a number being drawn from inside the circle will be the area of the circle. Okay, area of the circle divided by the area of the rectangle. Okay, so in this case you end up computing the area. So computing the area of this continuous domain is more like an integration here. You are not going to count how many dots are inside. Okay, rather because the concept of measure is now the area in the continuous case. So when you have to compute area, you will often invoke integration there. So in the sample space, S, if the sample space S is countable, then it refers to the discrete probability models. Okay, and as I said before, if we have like countable and then the cardinality of S is still infinity, so we still have to know how to handle those cases where we have countable but infinite, right? So we'll come back to that. But those are still classified into discrete case. Okay. And we know that we can we have probability of A will be sum of the probabilities of this SIs, okay, which are the outcomes in the sample space. Okay, so consider so this is a choice tree example. We have seen choice tree in a Galton board, but let us see another example of that. So consider 6 balls labeled 1, 2, 3, 4, 5, 6. And 2 balls are kept in two boxes. Okay, in the first box we have balls numbered 1, 2. Okay, and in the second box we have balls numbered 3, 4, 5, 6. Okay, so this is the box arrangement we have. So we have 1 and 2, and then we have 1 and 2 numbered marbles or balls, and then we have 3, 4, 5, 6 number in here. Okay, so let us assume the following. Okay, two boxes are equiprobable. Okay, so the fact that you can pick any of the boxes is equally probable. Okay, you don't have any preference here for the box. All the balls in each box is equiprobable. Also, all the balls in each box are also assumed to be equiprobable. So you don't have any case that ball numbered 1 is like really big compared to the 2 balls. So the probability of picking up the 1 ball may be a bit more. We are not assuming that. So among the box, picking 1 or 2 is equally probable, and in the box 2 also, probability of picking the balls number 3, 4, 5, 6 is equally probable. Now the question is, what are the probabilities P1, P2, P6? So what is the probability? Now assuming that all this information is given to you, so what is the probability that you will pick, what is the probability, what is the actual probability numbers P1, P2, P6 up to P6? Okay, so this is what we want to compute here. So we can make a choice tree. Okay, so this is an example where we describe choice tree. Choice tree will show up a little bit more into more interesting applications later on, but these are the basic applications you can think of. Many probability experiments are like sequence of steps that you do. The first step is the choice of the box, and the second step is inside you go again, and then you make another choice, and you can make another choice, and so on. Okay, so this is the way it happened in the Galton board example. A ball is hitting the first divider, and then it has to choose between the next set of two dividers, and so on. Okay, so this is just a simple example again of that. Okay, this is important. So what do we have? We want to compute the probabilities P1, P2, P3, P4, P5, P6, right? So that's our aim. And we are starting from our assumptions. So what we know is that P1 plus P2 will be half. Okay, so P1 plus P2 will be half. So in this case, because the probability that you will hit the box 1 is half, probability that you will hit the box 2 is half. So inside this, the probabilities of P1 and P2 are the sum, even though they may not be equiprobable, let us say, but the probability of P1 plus P2 should sum up to half. Okay, the probability of the childs should sum up to the probability here, right? So so this is what we know. Okay, P1 plus P2 should be half, and P3, P4, P5, P6 should be half. Okay, and the ball in the box and 1 are equiprobable. So this is something we are given already. And balls in box 2 are also equiprobable. So P3, P4, P5, P6 should be the same. And from above, we have these identities. So from using these two identities and then further information, we can conclude that P1 equals P2 equals 1 over 4. Okay, so from here we can use this two and then conclude that this is 1/4 and this is 1/8. Okay, so that's an example here. Now I will let us consider an interesting example here where we have the Stude prisoner problem. And this is an example here where we have a prisoner. Okay, so long time ago, let us say a prisoner was to be executed. Okay, long time ago there was a prisoner who was to be executed, and in response to his supplications, he was promised that in response to supplications, he was promised that he would be released if he drew a white ball from one of the two similar urns. Okay, so there are like urns. Okay, so or bag or okay, so this is urn 1 and this is urn 2. Okay, and there is a prisoner here. Okay, Okay, so this prisoner, so he was about to be executed, but then he was given a chance, so to say. So where he has to draw a white ball from one of the two urns. Okay, urn 1 and urn 2. The provisions were that he had to distribute 50 white balls and 50 black balls between the two urns. So in fact, he was also given the choice that in whatever way he liked, after which he had to draw a ball at a random from one of these urns. Okay, so then the question was, how should the prisoner put the balls such that the probability of his release is maximized? Okay, so I will draw this again, urn 1 and urn 2. And he has to pick the a white ball. Okay, but he is given 50 he is given 50 white balls, and he is given 50 black balls. Okay, so the choice, the way he is going to distribute the balls is up to the prisoner, which urn he should put more white, which urn he should put less white. It depends on the prisoner. Okay, so the question is, how should the prisoner put the balls in these urns such that if he picks the white ball, so if he drew the white ball, okay, then he is released, right? So he has to maximize the probability that he can pick the white balls. Obviously, when he distributes, okay, and after that he will be these urns may be swapped and so on, like they may be flipped and so on. So he will have no idea of where the urns, which side the urn is, the left urn or the right urn. So he will not know. Okay, so he will be blindfolded, and he has to pick the ball after that randomly. So he has to pick one of the urns. Okay, so this is like a choice tree again, like we saw just now. So the choice of picking the urn, two of the urn, because both the urns are of the same size, they're equiprobable. So these are like two similar urns. So he has no choice here. I mean, there's nothing skewed here. But what could be skewed here is inside what the way he puts the balls, right? So here, so far, if he starts with, and the probability of picking the one of the urns is like half. Okay. Now the question is, in what way he should distribute these balls such that the success that he have, okay, is maximized. Okay, the success of picking a white ball is maximized. So your focus should be on maximizing the probability of the white ball. Okay, so this is the problem you have. Okay, so I will leave you with this. You may think about this problem over. There will be no quiz now, so you can think over this problem of what could be the possible cases in this case. Okay, so what could be a good answer? Okay, so some of the strategies you can already think about is, let us say he puts all whites here. So let us say all white. Okay, and let us say in this urn he puts 0 whites, right? So let us say in this urn he puts all black. So from this, what is the what is the success, right? So let us say he did this and he is blindfolded, and these urns may have been flipped or randomly or something like that. So he has no idea which one is where. So in this case, there are two choices he has to do. So if he ends up choosing all white, then the probability of is like a half. Okay, the probability of choosing the urn 1 for him is half, and urn 2 is half. Okay, but if he indeed lands up in urn 1, then it is half, and then since it is all white, this is half times 1, right? And it is possible that he could have chosen the other urn, but then if he ends up choosing the other urn, he's surely going to lose. So here the probability of picking the white is 0. Okay, so you can define a parameter like this. So in this case, his success rate is like this, half. Okay, so now the question is, like, in what way you can do the distribution such that his success rate is maximized. So in this case, let us say he distributes all white here and overall success is half for him. But if he loses, like he loses badly, right? So he loses with a 50% chance is that he will lose. So the question is like, is there another way to distribute these balls in the urns such that his success is maximized? In other words, even if he loses, even if he misses to choose urn 1, even if he goes in the other direction, he still have some chance to pick some white. Okay, so another possibility you may think of already, which these are trivial possibilities, right? I'm asking for a solution where it is the best, right? So another possibility could be let us say you have like 25 whites. So 25 whites and 25 black, 25 white and 25 black. Now you apply the choice tree. So you went half here. Okay, you went half here. But then here now, since you also have a half number of the black, the probability of picking the white now becomes half times half. And similarly, if you went the other way, then it is half times half. Okay, so 1/4, 1/4. So probability of his having a success is like half again. Okay, so this half is same. Okay, so you did not increase his chance of release. Okay, and avoiding the execution. So you think about this. You can think iteratively. Like you may put all white and all black, start from here and see how the probabilities can be changed. Okay, and by doing some movement. Okay, so you think about this. Okay, and with this I will stop. And in tutorials you will do more fun problems like this. So I request you to do the tutorials as well. Okay, thank you. Bye.